Teuton Cosmonaut Productions presents Pyramids and Summations.
What's this? It looks like a big E.
This is called a summation sign. The way it's written right now, it means the sum of all the positive integers between 1 and 4. So this is equal to 1 plus 2 plus 3 plus 4. 1 plus 2 is 3, plus 3 is 6, plus 4 equals 10. The sum of all the positive integers between 1 and 4 is equal to 10. But now let's change it a little bit. Okay. What do you think this represents now?
It's the total of all the whole numbers from 1 to 100.
And what's the answer?
Who cares? I can get the answer on a spreadsheet.
But what if you're on a desert island without a computer and Dr. Evil won't let you go until you give him the correct answer? What would be your first step?
To catch a fish so I won't starve. That math is too tough.
But that question wasn't too tough for a kid named Carl Friedrich Gauss. In my first day in 7th grade, my math teacher, Mr. Jensen, told us a story about Gauss. When he was a kid, his math teacher asked him to add up all the whole numbers from 1 to 100. And Gauss got the correct answer in an instant. Now that really isn't too surprising when you consider that Gauss may have been the smartest human being who ever lived. Now, Mr. Jensen's intention was to get us to look for patterns in numbers. Now, Gauss actually lived a couple hundred years ago, so he didn't have the option of using a computer to get the answer. His thinking pattern went something like this. He listed all the whole numbers from 1 to 100. At least he did in his head, maybe not on paper. And he noticed a pattern. You could pair these numbers up. You could put together 1 and 100. That's the first pair. You could pair 2 and 99. You could put together 3 and 98, and so forth. Now, the total number of pairs of numbers is going to be half of 100, or 50. And each of these pairs is going to have the value of 1 plus 100, or 101. So, the sum of all the whole numbers from 1 to 100 equals 50 pairs times 101 for each of those pairs, or 5,050. That is the correct answer that Gauss gave his teacher. More generally, if you're adding up all the whole numbers from 1 to n, the number of pairs you'll have will be n divided by 2, and the total of each of those pairs will be what you get when you take n and you add 1 to it. So this is the general formula for adding up the first n positive integers.
That's pretty clever.
But maybe Dr. Evil would think that that last question is too simple. Think about this question. The sum from I equals 1 to 100, not simply of I, but of I squared. This would equal 1 squared plus 2 squared, dot, 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 all the way up to 100 squared. So what we're talking about is 1 plus 4, and then we're going to add 9 plus 16 plus 25, dot, 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 all the way up to 100 squared. What's the answer this time?
There's no way. It would be easier to catch a shark with my bare hands.
Well, if this is like catching a shark with your bare hands, let's make it a little simpler. We'll take this one step at a time. Let's start with a problem that's more like catching a puppy dog with your bare hands. Let's change this 100 to a 4. So now we're just going to be coming up with the sum of the squares of the integers from 1 to 4. And maybe while we do this, we'll see another pattern. Okay, here goes. Okay, now we're going to add up 1 squared plus 2 squared plus 3 squared plus 4 squared. 1 squared equals 1 times 1, which is simply equal to 1. 2 squared equals 2 times 2, which is also equal to 2 plus 2. Now, 3 squared equals 3 times 3, and remembering that multiplication is really multiple applications of addition, 3 times 3 is equal to 3 plus 3 plus another 3. 4 squared equals 4 times 4, which is equal to what we get when we add 4 plus a second 4 plus a third 4 plus a fourth 4. So the sum of the squares of all the whole numbers from 1 to 4 forms a nice pattern like this. Now here's how the movie began, with our friend Tutankhamun. And here's what's on the other side of that pyramid. Note that what we have on the pyramid is the same as we'd written on the whiteboard before. It represents the sums of the squares of the first 4 whole numbers. Now we have not one pyramid, but 3 pyramids. And right now they all look the same as the pyramid we were looking at a moment ago. So with each one of these 3 pyramids, the numbers that are displayed will add up to the sum of the squares of the first 4 whole numbers. Now we're going to take advantage of our visual aids to get a little bit tricky here. Obviously, we could rotate these pyramids without changing the sums of the numbers that are displayed on them. And that's what I'm going to do. I'm going to take this second pyramid and rotate it like this, so the 4s no longer are at the bottom, they're going down the left side. And we're going to rotate this one differently, so now the 4s are going down the right side. Earlier we were talking about pairs of numbers when we were looking at the sum of the numbers from 1 to 100 if you don't square them. Now we're going to be looking at triads of numbers. For example, if you look at the numbers that are at the tops of the 3 pyramids, we have a 1 and a 4 and a 4. They add up to 9. If you look at the numbers at the lower left of each pyramid, we have a 4 plus a 4 plus a 1. Again, they add up to 9. If you look at the numbers that are kind of in the center, you get a 3 plus a 3 plus a 3. Again, they add up to 9. They always add up to 9. And 9 is also equal to what you get when you take the number that's the last number in our series, double it, and add 1. Now the number of triads, as I'm calling them, is simply equal to the number displayed on each, or the number of numbers displayed on each pyramid, which is 10. 1 plus 2 plus 3 plus 4 equals 10. So what we have here are 10 triads, each of which adds up to 9. So let's summarize what we just saw. If n equals 4, in other words, if we're adding up the squares of the first 4 positive integers, and we lay it out in the shape of 3 triangles like we just saw, each triangle will have a total of 10 numbers in it. 1 in the first row, plus 2 in the second row, plus 3 in the third row, plus 4 in the fourth row will give us 10 numbers in each triangle. And we saw that each triad of numbers adds up to 9. So the total of all the numbers in those 3 triangles equals 10 times 9 equals 90. 10 triads, a total of 9 in each triad for 90. But 90 is actually equal to 3 times the sum of the squares because we had 3 triangles. So the sum of the squares is 90 divided by 3 equals 30. Let's check that. We're looking for 1 squared plus 2 squared plus 3 squared plus 4 squared, which is 1 plus 4 plus 9 plus 16, and that does add up to 30. So that gives us the sum of the squares of the first 4 whole numbers, positive whole numbers. But remember, that kind of is like catching a puppy dog with your bare hands. And our task is more like catching a shark with your bare hands. What we need to do, if Dr. Evil's going to get us off the island, is find the sum of the squares of the first 100 positive integers. And to do that, it's going to help if we can get a general rule. Here's the general rule. Okay. Now the number of numbers in each triangle, if you're talking about the sum of the squares of the first n whole numbers, is going to be equal to 1 plus 2 plus 3, all the way up to n. And to get that, we use the formula that we started with in this tape, which is you take n divided by 2, that's the number of pairs of numbers, times n plus 1, which is the total of each pair. So there are going to be this many numbers in each triangle. And the total of each of the triads is going to be equal to 2n plus 1. So the total of the numbers in all 3 triangles, if we're talking about the sum of squares of the first n whole numbers, is going to be this value here. It's going to be n over 2 times n plus 1, which gives us the number of numbers in each triangle. And then we have to multiply that by the value of each triad, which is 2n plus 1. But when we do this, we still have to divide by 3 to get our final result. And so the formula, which we've circled in red here, is the formula for the sum of the squares of the first n whole numbers. So we just showed that the sum of I squared from I equals 1 to n is equal to this value here. Using algebra, we can simplify this into the formula at the bottom of the whiteboard here. It equals n cubed divided by 3 plus n squared divided by 2 plus n divided by 6. I won't show all the steps of the algebra. You might want to prove it to yourself that we've done it correctly. Now let's test that formula in the case where n equals 4. We already showed that 1 squared plus 2 squared plus 3 squared plus 4 squared, it's going to equal 1 plus 4 plus 9 plus 16, which equals 30. Do we get the same result using our formula? Well, sticking in 4 in place of n, we'd have 4 cubed divided by 3 plus 4 squared divided by 2 plus 4 over 6, which equals 64 thirds plus 16 halves plus 4 sixths, which equals 21 1/3 plus 8 plus 2/3. And hey, that does add up to 30. Now, it doesn't prove the formula, but it's evidence that the formula may be correct.
But what if Dr. Evil wants us to go not just up to 4, but all the way up to 100?
Well, then you just do the arithmetic that's already written on the whiteboard and you get the answer.
But how am I going to do that on a desert island without a computer?
Well, just think about it for a second. How could you do it on a desert island? What tool could you use?
You could use the sandy beach as a writing pad?
Good idea.
And here's what you might see written on the sand.
But if you did it on the sandy beach, you wouldn't have to circle the final answer, which is 338,350. You wouldn't have to circle that in red. Hey, Gauss, thanks for getting us started.
Dr. Evil, let my people go.